In the voltage regulator circuit design and analysis example presented here, we have a 20 to 30 volt unclean, unregulated, varying input supply, and what we expect as the output of the circuit is 16 volt clean flat, and the capability of supporting or feeding up to 2 amp max to the load. For example, a heating resistive load like this one, RL. We want to figure out, given this limit that we are having as a spec for the regulator design, what is the mean max range for this RL that we can have and tolerate. And we want to also, given this spec and given the plan, we want to find the right value of components in this circuit like R1, R2, like RZ1, and also RE. So a couple of assumptions, and as well as RZ2. A couple of assumptions that I need to make. Let's make the assumption that this Zener diode that is shown here is, let's say, 3.6 volt Zener diode with 3.6 breakdown voltage. And let's make the assumption that this one is a 5.1 volt Zener diode. As an example, of course, just as a reminder, Zener diode is symbolically shown this way. So here is the cathode and anode of the Zener diode, as you can see here, with a circuit component. And then I'm just showing as an example a table from Vishay, which is sort of a distributor of the electronic components. In this case here, I just wanted to highlight that as an example. Of course, there are many of these, but as an example, the Zener diode voltages comes in specific values. Here is nominal values. Like for example, in this case, we are picking 3.6 volt. That's for one Zener diode, nominal, and then 5.1. Reason you see that this 5.1 is highlighted is because temperature coefficient for around 5-6 volt Zener diodes are very close to perfect, meaning that the variation of the voltage of Zener diode, so here is the Zener diode, and if you say, for example, nominal is 3.6 volt, the variation of this volt or breakdown voltage as a function of temperature is minimal for around 5 to 6 volt nominally, and below and above that it start increasing. For example, when you say a number like -9 and then 10 to the -4 per degree C, that means if, for instance, we're talking about 2.4 volt, the voltage of the Zener diode, the breakdown voltage, is changing by 2.4 times 0.0009, because it is -9, 10 to the -4. So it will change by, because of negative coefficient, so it will change and reduce by this much per degree C of temperature change. Let's say if temperature going up, the Zener diode voltage is going down by this much. So it basically sort of a sensitivity of the voltage of breakdown voltage of Zener diode as a function of temperature. The less this coefficient absolute value wise, the better. So with that in mind, we selected 5.1 and 3.6 for these Zener diodes, as you can see here in the circuit. So going back to what I have in my circuit here, okay, so here is 5.1, here is 3.6, and let's make the assumption that for this power transistor here in this Darlington transistor pair N-type, that this power transistor that is delivering the 2 amp max current, let's make the assumption that T1 has a practical, very practical beta or HFE of current gain of say 20, and for T2 let's make the assumption that beta 2 is 50. It's a low current transistor. For P-type, let's say bipolar junction transistor BJT T3, let's make the assumption since low current is also beta 50, and the same thing for this BJT transistor N-type T4. It's a low current one. I'm going to make the assumption beta 4 is 50 as well. Beta is the current of collector to current of base. Alright, so with that in mind, now that I have summarized the Zener diode voltages, let's dive into the circuit analysis. So let's first start with this Zener diode. We want it to be on during the normal nominal operation of the circuit. If it is properly biased, it requires a minimum. So let's make the assumption that for all Zener diode, the minimum current for being on, the minimum on current is 1 milliamp. So I need at least 1 milliamp through this guy. And when the transistor T4 is on, then it's supporting 1 milliamp here. Of course, there is a reliance issue with respect to this VBE, or base emitter voltage of this transistor T4, sensitivity to this one. So hence, one of the mechanisms to counteract that is via RZ2 that I'm going to talk about. But for now, let's focus on this transistor. So when it is on T4, you can see that, let me remove this beta because we know it's 50. So we can see that there is plus minus 0.7 volt voltage of base emitter diodic voltage drop there, PN junction. So from ground we go 5.1, then we go 0.7 volt. So therefore we get to, at base of transistor T4, we get to 5.8 volt. So 5.8 volt here at the base of transistor T4. Okay, the design of R1 and R2 should be in such a way that effectively they are in series. So that means they should be selected value-wise such that this current that is going through them is much larger than the base current of transistor 4. So IB4 should be considerably less than these guys. I'm going to write it this way. I want IB4 to be 1/100th of the current of R1 and R2, so that I can effectively neglect it and I can say R1 and R2 practically are in series. Alright, so if I make that assumption, what I can see is there is 16 volt across the series of R1 and R2, and I can say it this way: the current of R1 is practically equal to the current of R2 is equal to 16 volt divided by R1 plus R2 in series effectively. Okay, and the other thing I can see is there is 1 milliamp that is going through the emitter of transistor T4. Beta, which is the current of collector divided by current of base, is 50, which is roughly the current of emitter divided by current of base. So I can make the assumption that 1 milliamp, so therefore from here I can make the assumption that I base of transistor 4 is 1 milliamp, this 1 milliamp, which is approximate value for I of emitter, divided by 50 beta. So as a result, this IB4, the base of the current of base of transistor 4, is as a result of this is on the order of we're talking about 20 microamp. Now I want, as a result, I want IR1 to be 100 of that. So given that IB4 is 20 microamp, we understand based on this equation 1 that IR1 equal to IR2 should be 20 microamp, of course, times 100, which becomes 2 milliamp. So therefore I can write that this thing is equal to 2 milliamp, which gives me the sum of the R1 plus R2. So I can say R1 plus R2 as a result is equal to 16 volt divided by 2 milliamp, which is 8 kilo ohm. So I have the sum of R1 and R2 in this equation number 3. Let's say this one is 2. Okay, so I have the sum, but the other thing I can conclude is 5.8 volt here appears across R2 because the other side of R2 is grounded. So on one side I have 5.8 and on the other side I have ground. So across this R2 there is plus minus 5.8 volt. And through this R2 and R1 there is a 2 milliamp current that we just discussed is passing through them. So 2 milliamp current. Therefore I can easily find R2. So I can say R2 is that 5.8 volt voltage drop that I expect to be across, and 2 milliamp that is passing through. So as a result, it is equal to 2.9 kilo ohm. So that's the value of R2. Now, since I have the sum, equation 3, I have the R2, I can find R1 as well. So using combination of 3 and 4, I can find R1 should be equal to 5.1 kilo ohm, so that the sum of R1 and R2 is 8K. Okay, great. We found R1, R2. Now, one little last piece of this section is Rz2. To minimize the dependency of VZ2 1 milliamp minimum current support to be there as a function of whether T4 base emitter is properly there or not, if any fluctuation, we are providing one of the benefit of having this link here, that this wire, is also the fact that the 16 volt appears here nominal, and we have at this node at this node 5.1 volt. So across this RZ2 we have 16 and then 5.1. So I can select RZ2 in such a way that at least it provide 1 milliamp current, so that at least that 1 milliamp is coming this way as well as a backup. The fact that whether it become 1 plus 1 2 milliamp doesn't affect anything, because the maximum current that Zener diode can tolerate usually is on the order of 30, 40, 50 milliamp. So we are far, far lower than that. So everything is fine. I can say, let's set RZ2 in such a way that the voltage drop across RZ2 16 minus 5.1 divided by the current 1 milliamp, that is the minimal that I wanted to be there. So I'm setting it that way. So this is now obviously 10.9 volt divided by 1 milliamp. So it means that a good choice for RZ2 is roughly on the order of 10.9 kilo ohm, or 10 kilo ohm, let's say, a little bit even more than 1 milliamp. So roughly 10.9 or 10 kilo ohm. Okay, so that's my RZ2. So I can go say 10 kilo ohm. Okay, now we have selected these. What about RE, the value RE here? So let's see what's going on. If we have 16 volt, the value of load, of course, is easily computed at the max current. So I would say RL minimum, which happens when 16 volt is applied, max current, IL max, is 16 divided by 2, so 16 volt divided by 2 amp, which becomes 8 ohm. So the minimum acceptable load that we can put at the output of this circuit is 8 ohm. So load should be greater than equal to 8 ohm. Okay, that's about the minimum load. When that is the case, 2 amp is being supported and supplied by this emitter of transistor T1, high power transistor, and by a factor of 20, or 21 actually, we get to base, because this base of 1, so I'm going to write it here so that it's clear, IB1 is equal to IE1, which is the output current, divided by beta 1 plus 1. Because beta is collector to base. So from emitter to base, effectively, we need beta 1 plus 1. And then to get to IB2, I need to further divide it by another beta 2 plus 1. So I can say IB2 max is equal to I out max. And I can neglect, of course, the current, the 2 milliamp current going through R1, R2, or 1 milliamp or so going this way, compared to the 2 amp that is 1,000 times more than them. So I'm neglecting those little currents. So I out max divide by beta 1 plus 1 times beta 2 plus 1 in denominator. And we can write 2 amp divide by beta 1 plus 1 is 20 plus 1, 21. And then we have 50 plus 1, 51. This roughly becomes 1.9 milliamp. So maximum base current that need to be there at the base of transistor T2 is 1. Milliamp to support the 2 amp max that is desired for this circuit. There is 1 milliamp going this way, so, and maximum 1.9 milliamp going this way. So therefore the maximum current that is coming from collector of this p-type BJT is 1.9 plus 1, which is 2.9 milliamp. Okay, this 2.9 milliamp should also come this way. So basically what I'm saying is the current that is going through RE in this scenario maximum current that RE needs to support is 2.9 milliamp. So all I can say is the current of resistor RE is equal to the voltage drop across RE. So let's first write it down. I'm just saying 1 milliamp, which is this current needed for transistor T4 and the Zener diode, plus the 1.9 milliamp. So this one is IT4, and this one is IT4. This one is IB2 max. IB2 max. I'm talking about, if the color change helps, I'm talking about this 1.9 milliamp here. So let me just clearly write it. 1.9 milliamp, and this 1 milliamp here. The sum of these two guys is the current that is going this way, 2.9, which is the same current as RE, so is equal to 2.9 milliamp. Now let's take a look at the voltage drop across RE. So worst case scenario, this unregulated, not clean supply at lowest is 20. It's varying between 20 and 30. So at lowest we have 20 volt here. Since we have 20 volt, then we have 3.6 volt drop across reverse voltage of the Zener diode. So this node minimum will be 16.4 volt. There is also a plus minus VBE of voltage of emitter base of this P-type bipolar junction transistor, which is 0.7 volts. So if we go up naturally from this point to 0.7, we can see that effectively it's the voltage drop across this resistor is simply just 3.6 volt minus the 0.7 volt that we see here. So it's 2.9 volt. So again, it is because of 3.6 minus 0.7, the voltage drop across the emitter base of the P-type bipolar junction transistor. So there is plus minus 2.9 volt across this RE. So what is the benefit of this observation? The benefit is I can say that RE is equal to voltage drop across RE divided by the current of RE that we just computed here. So it is 2.9 volt divided by 2.9 milliamp. So we are dealing with roughly 1 kilo ohm for RE. Okay, so we found RE as well. We better set it to 1 kilo ohm, and we are all set in order to just provide up to 2 amp max. Of course, the circuit won't be able to provide more than 2 amp via the cascade of these transistors. So now with that said, the only thing that is remaining is this RZ1, and that is not difficult. You can see that the current planned, as we discussed, for RE, or basically for emitter of transistor T3, is 2.9 milliamp. The beta for T3 is, so the beta for T3 is 50. So if there is a current of 2.9 milliamp going through, so let me just clean up. If the current of 2.9 milliamp going through the emitter of T3, the base of this transistor, so the base of this transistor is having a current like this one, IB3, that is emitter current, collector current, sorry, this is collector. So collector current 2.9 divided by beta, which is 50. So that is on the order of, let's say, 3 divided by 50, roughly 60 or 58 microamp. So you're talking about 58 microamp that is going this way. And practical design, if we support, let's say, a current of 58, let's say 10 times that, which is 5.8 milliamp. So if I have, let me change the color so that it's easier to see what I am talking about. So if I set the color, let's say if I set the current going this way 100 times more than this, so 100 times more than 58, meaning that at least 5.8 milliamp current through RZ1. then as a result we can neglect the impact of this, and we can say the current through RZ1 is fixed, say even at 6 milliamp. So as an example, I can just say, okay, let's set the current of IZ1 for the Zener diode Z1 at, say, 6 milliamp, which is good enough practically. So minimum voltage across RZ1 is 16.4, and on the other side we have 0. So I can say, in order to guarantee that through RZ1 I have 6 milliamp minimum, then I can say RZ1 is equal to 16.4 volt divided by the current of 6 milliamp that is planned. So the current of 6 milliamp. Okay, so this translates to roughly 2.7, let's say, kilo ohm, roughly. So as long as I set the value of RZ1 to around 2.7 kilo ohm or even a little bit higher, then the current value should be fine. Diode Z1 is guaranteed to be on without any problem. So that is what I'm trying to guarantee. So that is a good choice. This finalized the discussion about the choice of parameters and the value of parameters for this simple, of course imperfect voltage regulator example design. The actual practical design require more components in terms of protecting the supply voltage and protecting the output transistor not to burn when the RL goes below, let's say, if the output is shorted or RL becomes less than what is the acceptable value. In this case, if you reduce RL below the 8 ohm that is allowed, then the circuit is not able to provide the current, and hence the beyond that, for RL less than 8, there is no guarantee for 16 volt to be protected. So the voltages start dropping actually, because these transistors are not able, according to this design, to provide more than 2 amp. So if you reduce RL below 8 ohm, then the circuit starts failing in the sense that the output voltages start dropping. And of course RL can go to infinity on paper, so we can open basically here and have RL effectively infinity, because in that case the only thing that transistor T1 is sending out is 2 milliamp for the series of R1 and R2 and 1 milliamp for RZ2, and that's fine. There is nothing wrong about that. So RL can be at least 8 and up to pretty large values. So that's the conclusion here. I hope that this example is helpful in terms of showing how at least we can have the basic set of components to design a voltage regulator without op-amp, even though it lacks some number of good protective features that a good voltage regulator need. But I think it's good enough in the sense of covering how we can start from a very unregulated voltage of 20 to 30 volt and then get to a very flat and fixed 16 volt voltage guaranteed by the feedback in this circuit. I hope this example is helpful.